In this video, we're going to talk about electron configurations for ions. For anions, electron configurations are straightforward. You use the same rules you would use for an atom, but you add additional electrons, and they fill in the order predicted by the Aufbau principle. For example, what is the electron configuration for the phosphide ion, which has a 3 negative charge? It has an atomic number of 15, so when it becomes an ion, we add 3 more electrons. That's going to give us 18 electrons. Now, the first thing we're going to do is write the electron configuration for the parent atom phosphorus. So we get 1s2, 2s2, 2p6, 3s2, 3p3. The next thing we're going to do is add the 3 electrons to make it the phosphide ion. And we just add those 3 electrons into that 3p subshell so that we have 1s2, 2s2, 2p6, 3s2, and 3p6. This is fairly straightforward. However, things are a little different when we get to cations. For atoms in the first 3 rows, it's not too difficult because here the electrons that were added last will be the first ones removed. However, when you get to the 4th row, especially when you get to those transition metals, the electrons that need to be removed may not be the ones that were most recently added. For example, although the 4s electrons fill before the 3ds, the 4s electrons are outer electrons, and the outer electrons, the valence electrons, are going to be the ones that are removed first because they're easier to remove than the core electrons. Let's look at some examples. We're going to first start with an easy example, sodium, which has an atomic number of 11 but has 10 electrons when it ionizes. The first thing we're going to do is write out the electron configuration for the parent atom sodium. 1s2, 2s2, 2p6, 3s1. Now, sodium loses 1 electron, and we are going to subtract the electron from that 3s orbital to get 1s2, 2s2, 2p6. And yes, we've lost that 3rd shell, and this is not unusual when you're making cations. We're going to do another easy example. We will do the aluminum cation. Aluminum has an atomic number of 13. When it ionizes, it loses 3 electrons. So, to find the electron configuration, we're going to first write out the configuration for the parent atom. For aluminum, it's 1s2, 2s2, 2p6, 3s2, and 3p1. And then we're going to subtract 3 electrons from this, and our electron configuration is now 1s2, 2s2, 2p6. And you'll notice that as for sodium, we totally lost our 3rd shell here. Now, let's do a harder example. We're going to do iron, and we're going to do iron in 2 ways. Because iron can form a 2+ ion, it can also form a 3+ ion. Let's start with the 2+ ion. Our atomic number is 26, and the first thing we're going to do is we're going to write the electron configuration for the parent atom. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. And if it helps you to make the 3ds and the 4s's switch places so that the 4s's are on the outside, that is fine. You don't have to do that. But if it makes it easier for you, you can. So to get iron 2+, we are going to subtract 2 electrons, but we're going to take them from the 4s orbital. Remember, the 4s electrons are the outermost ones, and they're the valence electrons for iron. So our new electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, and we've lost our s electrons. Now, we're going to do the same thing with Fe3+. First, we're going to write out the electron configuration for the parent atom, just like we did before. Then we have to subtract 3 electrons now, and we're going to subtract 2 of them from the 4s orbitals, but we also have to take 1 from the 3d orbital. Our final electron configuration for iron 3+ is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. Now here's a periodic table that divides the elements into different blocks. We have the S block, the P block, the D block, and the F block. And this is a very useful table for helping you to explore the electron structures of the various parts of the periodic table. In summary, electron configurations for ions are a little different. The electron configuration for anions is pretty easy. Just write out the electron configuration for the parent atom and add the extra electrons using the regular Aufbau filling orbital. Writing electron configurations for cations isn't too bad if you're dealing with the first 3 rows. You just write the electron configuration for the parent atom and remove the electrons you need to remove. However, when you get to the 4th row, where you also have d orbitals that are being filled, the 4s electrons are going to be removed before the 3d electrons, even though the 4s electrons weren't the electrons that were added most recently.